Today we're going to discuss numerical error in Euler's method. Before we do so, let's review some ideas behind periodic forcing of nonlinear systems and chaos. Recall that we considered the forced harmonic oscillator, which we can write in the form y double prime plus p times y prime plus q times y equals epsilon times cosine omega t. The amplitude of our forcing term, epsilon, can be thought of as a small non-negative number. Here, omega will be the frequency at which we're forcing. Let's assume that our coefficients p and q satisfy p squared minus 4q is negative, so that the roots of the characteristic polynomial are complex numbers. That is, lambda equals alpha plus beta times I. In this case, we can write the general solution as a combination of e to the alpha t cosine beta t, e to the alpha t sine beta t, and an amplitude capital A times cosine omega t minus a phase angle phi. Assuming that our system is undamped, that is, p is equal to 0, we find that q is equal to beta squared. Here, beta is the natural frequency of the system, and the phase angle phi equals 0. In this case, the general solution is y of t equals k1 times cosine beta t plus k2 sine beta t plus an amplitude epsilon divided by beta squared minus omega squared times cosine omega t. Here we are assuming that omega, the forcing frequency, does not equal beta, the natural frequency, so that we are away from resonance. We can then express our second order differential equation as a two-dimensional system. Let's write this as dy dt equals v, so that dv dt equals negative beta squared plus beta squared times y plus epsilon cosine omega t. When our forcing amplitude epsilon equals 0, we have a Hamiltonian system. That is, we can find an energy function h so that F is the partial of h with respect to v, and g is negative the partial of h with respect to y. Let's observe that the level curves, namely h of yv equals c, are just circles and ellipses. Here in the lower left, you can see what happens when epsilon equals 0. We have a nice circle, and everything seems to oscillate in a periodic fashion. On the other hand, when epsilon is just a little bit above 0, then we can see that our solution seems to, quote, wobble, unquote, around the level curve corresponding to h equals c. In 1918, the German engineer Georg Deffing was interested in generalizing the forced harmonic oscillator. He considered the equation y double prime plus p times y prime plus q times y plus r times y cubed equals epsilon cosine omega t. We nowadays call this the Deffing oscillator. Here, p is the damping coefficient, q is the spring constant, and r can be thought of as nonlinearity in the restoring force. Just like with the forced harmonic oscillator, we can express the second order differential equation as a two-dimensional nonlinear system. That is, dy dt equals v, so that dv dt equals negative p times v minus q times y minus r times y cubed plus epsilon times cosine omega t. We only focus on the case that is undamped, that is, p is equal to 0. When the forcing amplitude epsilon equals 0, we always have a Hamiltonian system. That is, just like before, there is an energy function h, so that F is the partial of h with respect to v, and g is the negative the partial of h with respect to y. Since we are assuming that q is positive and r is non-positive, let's set q equal to beta squared. Again, beta is like the natural frequency of the system, and r is negative beta squared over lambda squared. In this case, we find that there are three equilibrial points, namely the origin, 0, 0, which turns out to be a center, and two saddle points, plus or minus lambda, comma, 0. This all explains what happens when epsilon is equal to 0, but we are interested in solutions y of t for small positive epsilon. We found before that when we have a forcing function g of t equals epsilon cosine omega t, then we can find numerical solutions for our displacement y of t and velocity v of t. In fact, the function g of t is periodic with the period 2 pi over omega, so we'd like to measure whether our solutions, namely y of t and v of t, are also periodic with the same period. In this sense, we define what's called the Poincare return map. That is, by looking at various integer multiples of the periods, we can actually see whether our functions y of t and v of t return back to the same point at which g of t also returns to. We actually found by looking at various graphs that as the forcing amplitude epsilon increases, the behavior of this Poincare return map became less and less predictable. This is known as chaos. Today, we'd like to focus on the numerical error in Euler's method. Let's first explain things by kind of going over a review of what we've discussed so far here in the course. Throughout this course, we have considered various initial value problems as we did in lesson number 11. Here we have dy dt equals a function f of t comma y, where we'll think of capital Y as an n-dimensional vector, consisting of the functions y1, y2 through y sub n. In fact, in lesson number 5, we proved the following result for one-dimensional systems. We call this the existence and uniqueness theorem. Let's consider a first-order differential equation of the form dy dt equals f of ty, where y of t0 equals y0. Let's say that there is a rectangle consisting of pairs t and y, where t is between a and b, and y is between c and d, such that f is continuous on this rectangle, the partial of f with respect to y is continuous on this rectangle, and the initial point t0, y0 is contained in this rectangle. Then there exists an interval I containing the initial time t such that this initial value problem has a unique solution y of t defined for all t in this interval. In fact, we should point out that in lesson 15, we stated and proved a similar result for two-dimensional systems. Now, in all of this, we note that we can only find an explicit y of t in just a few cases. So instead, we're interested in finding approximate solutions. In lesson number 4, we introduced the following, which we called Euler's method. Again, let's consider a first-order differential equation of the form dy dt equals f of ty, where y of t0 equals y0. We'll fix a step size h and recursively perform the following 4 steps. First, compute the slope f of tk yk. Second, compute the time t sub k plus 1 equals tk plus h. Third, compute the value y sub k plus 1 equals yk plus the slope times the step size. And finally, return back to step number 1 with k replaced by k plus 1. A plot of the points tk, yk will be an approximate plot of the graph of the actual solution y of t. This technique for finding an approximate solution is known as Euler's method. And in fact, in lesson 14, we generalized this to two-dimensional systems by introducing what we called Euler's method for systems. Here's an example of Euler's method. Let's consider the first-order equation dy dt equals 2y minus 1, where initially y of 0 equals 1. Back in lesson number 4, we found the actual solution y of t equals e to the 2t plus 1 divided by 2. Here on the screen, you can see how we've worked out the numerical scheme of the various time steps t sub k, the approximations y sub k, the exact values y evaluated at t sub k, and the errors by looking at the absolute value of the exact value, y of t sub k, minus the approximate value, y sub k. One of the things that we notice here is that even though the approximate value, y sub k, is very close to the actual value, y evaluated at t sub k, we see that the total error increases as k itself increases. Here is an example of the plots that we find by using Euler's method. On the left, here's an example of Euler's method for the step size h equals 0.10. The blue line is a plot of the actual solution, whereas the gold dots are just the points that we found on the previous slide using Euler's method. On the right, we have a much better approximation by choosing a smaller step size. On the right, h equals half of what it was before, namely 0.05. Here you can see not only are there more gold dots, but the gold dots have a better approximation. They are better placed towards the blue line, which is the actual solution. These two plots here lead a series of motivating questions. First, how accurate is this method? That is, can we measure how the total error grows as a function of the step size h and maybe even the index k? Second, are there other methods which do a better job of approximating the actual solution y of t? Here we present the main result with regard to these questions. As before, let's consider a first order equation, dy dt equals f of ty, where y of t0 equals y0. Let's say that there is a rectangle R where t is between a and b and y is between c and d, satisfying the following criteria. First, f is continuous on this rectangle R. Second, the partial derivatives f with respect to t and f with respect to y are both continuous on this rectangle. And third, the initial point t0, y0 is contained in this rectangle. We know from the existence uniqueness theorem that there is a unique solution for this system. But moreover, let's say that we try to find an approximate solution using Euler's method for some step size h. The main result here states that there exist constants m1 and m2 such that the error, namely the absolute value of y evaluated at tk minus y sub k, is less than or equal to a constant times the step size h. This constant is m1 divided by twice m2 times the exponential e to the m1 times b minus a minus 1. Notice that this is true for all indices k being 0, 1, 2, and so forth. In fact, the total error really only depends upon the length of the interval from a to b. Remember that this is the region for the time, and the step size h. We actually see from this formula that if the step size h is decreased, then the error decreases linearly. That is, we have a bound of the form, the error e sub k is less than or equal to c times the step size delta t for some constant c. Let's spend the rest of today's lesson going over the proof of this proposition. We're going to prove this by introducing a series of three lemmata. These are just simply smaller statements that we can combine together later to form a larger statement, such as the previous proposition. The first of our lemmata states, there exist constants m1 and m2 such that for any non-negative integer k, we have the inequality that you see here on your screen. Let's sketch over why this is true. First, notice that if y of t is our unique solution, that we can compute the derivative in terms of f, and therefore the second derivative of the solution in terms of the partial of f with respect to t plus f times the partial of f with respect to y. Now, performing a Taylor series expansion around this step size h, we then find that we could write y of t plus h as y of t plus f times h plus 1/2 partial of f with respect to t plus f times partial of f with respect to y times h squared, plus some higher order terms. In particular, if we let m sub 1 be the maximum on this interval of partial of f with respect to t plus f times the partial of f with respect to y, then we find the inequality y evaluated at t plus h minus y of t minus f times h is less than or equal to m sub 1 times h squared over 2. Notice that this is true for all t and y in our interval in our rectangle R. On the other hand, remember that we have Euler's method, which means we can define y sub k plus 1 minus y sub k in terms of the slope f of tk yk and the step size h. Using all of this, we can write a slightly fancy identity that explains how y evaluated at tk plus 1 minus yk plus 1 can be expressed in terms of this slope that we just explained and the difference y evaluated at tk minus y sub k. Plugging this into the expression that we had before, we now find an inequality that relates the error term at k plus 1 and the error term at k. Again, we use another Taylor series expansion, this time for the function f around the y variable, to then find that we have the inequality, the absolute value of f minus f evaluated y sub k is less than or equal to m sub 2 times the absolute value of y minus y sub k. Here, m sub 2 now is the maximum value of the partial of f with respect to y on the rectangle R. Putting both of these together, we now find the desired inequality as stated before in lemma 1. Now let's state lemma 2. This says for any non-negative integer k, we have the following inequality in terms of the error absolute value of y evaluated at tk minus y sub k. To see why, let's denote z sub k as pretty much the left-hand side divided by the right-hand side. And let's let capital K be 1 plus m sub 2 times h. Notice that the inequality in lemma 2 is equivalent to writing z sub k is less than or equal to capital K to the lowercase k minus 1 divided by capital K minus 1. Simply put, we're going to prove all of this by induction. Let's observe that lemma 1 can be restated to say z sub k plus 1 is less than or equal to 1 plus capital K times z sub k. The base case is rather easy because when lowercase k equals 0, we see that z sub 0 equals 0. If we assume now the inductive hypothesis, we can focus on the inductive step. Here, the k plus first case, we can write as z sub k plus 1 is less than or equal to 1 plus capital K times z sub k. But now using the inductive hypothesis, z sub k is less than or equal to capital K raised to the lowercase k minus 1 divided by capital K minus 1. Using some algebra, we now find that z sub k plus 1 is less than or equal to capital K to the lowercase k plus 1 minus 1 divided by capital K minus 1. So the kth case implies the k plus first case, meaning that we have indeed proved the inequality in lemma number 2 by induction. Finally, we focus on lemma number 3. This is exactly the inequality that was stated in the proposition. The idea here is that we will divide the interval from a to b into n equal parts. That is, our step size h will just say take the length of the interval for t, that is from a to b, and then divide this by n. We see, or at least we've seen from some of the graphs from before, that the largest error is the difference that occurs at the end of the region, namely when k is equal to capital N. This means that the error, namely y evaluated at t sub k minus y sub k, is less than or equal to the expression that you see here on your screen. Now, if we realize that 1 plus x over n raised to the n is approximately equal to e to the x, our exponential, then we can piece all of this together to see that our error term divided by h is less than or equal to the constant that we discussed before, m1 divided by twice m2 times e to the m2 times b minus a minus 1. This concludes the proof. Thanks very much for watching.